Hello all, I am Karthik KR, an engineering student from BMS College of Engineering, pursuing my bachelor's in the Electronics and Communication stream. Today, we shall discuss the concept of wave-particle duality. But before dealing with it, let's visit history to see how this dilemma even came up. Light is an interesting phenomenon. For billions of years, light has been that singular source of energy capable of sustaining life as we know it. But the discussion on light was never considered significant until the early 17th century. From this point in history, light has always been a matter of controversy. When Isaac Newton proposed his famous corpuscular theory, it became a prevalent and predominant theory through a large part of the 17th century. The corpuscular theory put forth that light was composed of small, discrete particles that follow a rectilinear path with finite velocity. At around the same time, Christian Huygens had a contradicting philosophy and claimed that light behaved as a wave and not a particle. This theory, today known to us as the Huygens wavefront principle, however, failed to come to light during Newton's time, much due to his overwhelming popularity and influence. But physics took a turning point with the discovery of interference by a British physicist and physician Thomas Young. The widely accepted corpuscular theory saw its downfall because Huygens' principle was capable of explaining the phenomenon of interference. For almost 200 years, Huygens' wavefront principle was used as a basis to prove the wave nature of light. In 1905, Albert Einstein changed the perception of reality with his groundbreaking discovery of the photoelectric effect, for which he was awarded a Nobel Prize. The reason why this phenomenon became very important was that it could be explained by the particle nature of light, where light behaves as particles called photons. At the same time, the wave nature of light could explain phenomena like interference, diffraction, as well as polarization. This created an ambiguity, challenging the nature of light. While the wave-particle duality dilemma for light was causing confusion, it was soon discovered that the same was true to many other subatomic particles. For instance, Davison and Germer's experiments proved the wave nature of electrons, while the cathode ray tube experiments stood as strong proof for its particle nature. In 1924, while Niels Bohr was proposing his atomic model, a young scientist by the name Louis de Broglie hypothesized the dual nature of matter from Bohr's theory. Louis de Broglie proved his proposal through a simple equation that related both particle and wave nature. With this equation, he showed that the wavelength of light associated with the particle was equated to Planck's constant over the momentum of the particle. His equation related many other wave properties such as amplitude, wavelength, frequency, etc. to particle properties such as mass, velocity, momentum, and so on. Then, how do we visualize this nature of all matter? It is imperative to understand that the wave or particle nature is a representation of the abstract probability function or wave function that is derived from Schrödinger's wave equation. Schrödinger's wave equation asserts the dual nature of matter and determines the nature at any given point as a function of probability of various factors. This concept soon exposed scientists to the modern quantum world. Thus today, the question of whether matter is a wave or a particle is completely redundant. We understand that it is energy that manifests itself into a form convenient for its existence, and its nature as viewed by us in all probabilities is not its nature, because we transmit and receive energy in order to perceive it, and are thus altering the conditions in which we wish to observe matter. This is the fundamental logic behind Heisenberg's uncertainty principle. It would be safe to assume that we cannot perceive matter under specific conditions, as we affect those very conditions by intruding into the system, and these erroneous observations cannot lead to a conclusive result on the universal nature of matter.